Hello, everyone. Good afternoon, good evening, good morning. My name is Berk Geveci, and I lead the scientific computing team here at Kitware. So I get the pleasure of doing the introduction for this webinar. We're going to talk about Catalyst and a little bit about ParaView Catalyst. These are our open source platforms for doing in situ analysis and visualization. I will start with a very brief introduction to Kitware, and then Corey is going to do the fun part and talk about the technical aspects. He will start with a high-level overview of in situ analysis, and then the rest is going to be essentially a deeper dive into how to integrate Catalyst with your simulation. If you're interested in getting an overview of what Catalyst is, what it can do, etc., we have a previous webinar on the topic. If you haven't seen that, you may want to go watch the recording for it. During the webinar, if you have questions, there is on the upper right, I think it's the same for all browsers and interfaces. There is a chat bubble that you can click on and then ask questions. And then we will take quick breaks to answer those questions. Maybe I'll answer some of them also by typing. And also at the end, we will answer questions. So now we can go to the next slide. So Kitware is a leader in scientific computing and AI research and development. We partner with government agencies, industry leaders, and academic institutions to solve complex challenges in areas of computer vision, medical imaging, scientific computing, and high-performance software systems. Our mission, to summarize, is to build cutting-edge open source tools that accelerate discovery and empower innovation. So we have a decent-sized team, over 150 engineers, researchers, and developers, and we're spread across 6 offices. These include New York State, North Carolina, New Mexico, Virginia, Minnesota, and then in France, in Lyon. This distributed collaborative culture helps us deliver impactful solutions on a global scale. At the heart of our philosophy is the deep commitment to open source. We believe in building sustainable platforms that bring communities together, platforms like Tram, ParaView, and today's Spotlight Catalyst. These tools are not just to solve problems, but they are also there to encourage collaboration, accelerate progress, and they form the foundation of the next generation innovations. Next slide, please. There it goes. So as I mentioned before, we're a highly collaborative company. Our largest research efforts are generally funded by the US federal government and involve many commercial and academic partners. We're also involved in smaller research efforts. We perform custom application development, and we also provide support and training on our open source platforms. Our areas of expertise span energy and manufacturing with a focus on simulation workflows, high-performance computing, scientific visualization, and data analysis. We also work in healthcare and life sciences with a focus on digital pathology, surgical planning, medical image analysis, medical visualization, and bioinformatics. For our defense and intelligence customers, we work in the areas of visualization, data analytics, image and video forensics, threat detection, and activity recognition. And deep learning is a large part of what we do, and we have a strong emphasis on ethical and explainable AI. So that was a whirlwind introduction to Kitware. So next, I'd like to introduce Corey Wetterer-Nelson. He is our lead for Catalyst, and in a minute is going to take from here. For those that just joined, I just want to remind that we're going to take short breaks to answer questions. There is a question chat bubble on the upper right. You can click on that, type your question, and then we will take either quick breaks or we will try to answer the questions at the end. So with that, I'm handing to Corey.
All right, thank you so much, Berk, for that introduction. So for the rest of this presentation, we're going to be talking about Catalyst, in situ analysis, and how to get going with the Catalyst API in your own simulation code. For the most part, this sort of tutorial is going to be covering specifics in detail, but we're also going to be glossing over a bit of implementation details that are not super core to sort of the mission here for what we're trying to get across. But for that kind of detail, we actually do have a pretty detailed guide on our website that we'll be showing at the end. So if you want to follow along, ask questions. If we gloss over something that you want a little bit more detail on, please let us know, and we're happy to either go back or plan for providing more information in the near future. But let's get going. So to start, we're going to talk about what in situ analysis is, and especially for those who are uninitiated, hopefully we can convince you that this might be something to look at for your simulation workflow. So what is in situ analysis? So this is kind of a concept of concurrently computing analysis and visualization tasks while a simulation is running. This is really a response, a workflow response to the growing I/O bottleneck in high-performance computing, where simulations are able to produce so much more data than existing I/O capabilities can write to disk in a reasonable manner. Simulations are able to generate terabytes and petabytes of data, and storing that data can be very untenable. So that's where in situ analysis comes in. Here we try to take as much of what you would typically, in a typical sort of workflow, the sort of post-processing analysis that can be done using tools like ParaView for computing different data extracts, integrating various quantities of interest, etc. We take all of that capability and power and bring it into your simulation through Catalyst. So today we're going to be talking about sort of the basics of getting started on how to use that, and we're going to be focusing on this sort of in situ workflow. You'll see that there's also a related workflow of in-transit analysis, which is a process of actually moving or copying your data across a network to another compute resource for asynchronous processing. And we won't be covering that, but if you're interested, please let us know, and we'd be happy to dig into that in a future webinar series. So a lot of benefits to in situ analysis. The first up is kind of a basic one, but quick and easy runtime checks. And this is simple, but very valuable, I think, to especially getting going with new experiments in simulation science. This provides access to image outputs, which might be difficult to get from a simulation out of the box, which can identify very quickly incorrect behavior while a simulation is running. Further advanced analysis to identify things like divergence or undesired or poor configurations. These can be identified much more quickly than if you were to rely on simple statistics about your output that your simulation might be generating for you. Further computational monitoring and steering, even, that is the process of actually human intervention into a simulation at runtime, can be used to combine compute and human input very efficiently. Further, we get because in situ processes run on the same in the same memory space as your simulation, we have access to the full simulation data which is significantly more than what is typically economical for you to save to disk. So that means we can effectively get better insights. We can get higher frequency outputs. We can do more in-depth analysis in time temporally than we could if you're simply saving out restart files every tens of thousands of time steps, for instance. And that leads to faster time to insight. We can have certain configurations run faster because I/O costs can be one of the most taxing parts of a simulation workflow. And so because we can replace much of the I/O cost with compute, that compute can run much faster, and we get faster time to the actual output that we desire from our simulations. And further, we can actually accelerate post-processing as well. So because we have this flexible API for generating data extracts from your simulation data, you are able to produce these sort of in between data sets that are much, much smaller and can be processed much more quickly after the fact, but still gives you this sort of exploratory analysis that you might desire from your typical post hoc analysis workflow. And this altogether leads to a more efficient use of HP systems. Because we can replace slow file I/O with faster compute operations, we can take advantage of the raw compute power that you have for your allocation, rather than wasting valuable wall time on writing very large files to disk. We can spend that time doing compute and getting to that insight faster. Further, for things, if you have access to heterogeneous systems, which is kind of the norm at this point, taking advantage of GPUs and CPUs concurrently, in situ computations can be used to better saturate your compute allocation, taking advantage of underused or underutilized resources that your simulation might be not taking advantage of fully. Now, this is where Catalyst comes in. Catalyst has really led the in situ computing really since the beginning. This is a production-ready software that you can plug into your simulation workflow today and be up and running with in situ analysis fairly quickly. We've demonstrated it running on millions of MPI ranks on all of the biggest computers in the world, including the Frontier supercomputer at Oak Ridge National Lab, the first exascale computer in the US. It's been lauded by many organizations for producing high-quality visualizations, including various Editor's Choice awards through the years. Again, more Editor's Choice, more Reader's Choices. We are tied for ParaView, which is, as you'll see, a closely integrated software platform with Catalyst. And we can use this on pretty much any HPC architecture that you can throw at it. I will be demonstrating using Catalyst on my MacBook, but if you have access to an exascale computer, it runs there as well, performant. All right, so now we can get into some nitty gritty. Like I said, this tutorial is not really meant to be followed along step by step with your own code in front of you. So you can sit back, listen. If you have any questions, please post them in the chat. We're happy to answer them. And if there's anything that that I might be glossing over that you might be interested in a deeper dive, please let us know, and we will see if we can add it to our list of future webinars. All right, so to get started, we're going to need a software environment that is pretty standard at this point for this sort of simulation computing. If you have access to Git, I assume you might. CMake is our preferred build platform for both Catalyst and ParaView, as well as many simulation codes out in the wild. Here at Kitware, we really like the Ninja build system, but if you are a fan of Make, please be our guest to use that. It should work out of the box. As we are targeting sort of high performance computing, of course, MPI is an option that we can explore. We won't be looking at our MPI options today, but that's an optional, that is an optional piece of your environment that you can set up. And of course, this is all going to be in C++ today. If you're interested in codes that are built on top of Fortran or Python, let us know. All right, so to start off, we need a simulation. So we're going to be looking at LULESH, which stands for the Livermore Unstructured Lagrangian Explicit Shock Hydrodynamic Code.
Can I interrupt you for a second?
Absolutely.
There's a question before we start LULESH. Okay. I think it's relevant. And the question is it possible to call your libraries from a Python PyTorch script running a deep neural network? And would this constitute in situ workflow? Do you mind if I answer that question?
Absolutely, yeah.
So I would say yes, that constitutes an in situ workflow. However, since you're already in Python, there is no need to use Catalyst. You can actually directly invoke ParaView Python by importing ParaView into your Python environment, passing data to it, and calling it. And the passing data may get somewhat involved. In that case, actually using the Python interface of Catalyst may make things easier in some ways. We won't get into a lot of details of how to do that, but actually, if you look at the examples, in the repository, there are some examples of Catalyst being called from a Python-based simulation by using NumPy to essentially pack the data into what Corey is going to describe here and calling Catalyst.
Awesome. Yeah, thank you, Berk. So let's see. So we're back to Lulesh. So this is going to be our model simulation code. It is a very stripped down simulation code. It only solves one single problem, but at resolutions that are user specified. Takes advantage of a regular Cartesian grid, although it's technically under the hood an unstructured grid. We are going to simplify that for the purposes of our Catalyst integration here. This was a code that was developed at Lawrence Livermore National Lab to be sort of a proxy code that could be scaled to very, very large heterogeneous machines, but it also can run on a MacBook. So it's a really good sort of example code for the type of integration that we care about, and we'll talk a little bit more about that. So this solves a simple set of blast problem, which is an explosion that takes place at the origin. This is symmetric about the X, Y, about each of the cardinal planes. We have this kind of spreading out of material through this domain. The mesh is actually deformed as this blast occurs. But it's it's a simple example, but as we'll see, it provides enough complexity that we can kind of dig into it. So despite it being a simple sort of problem, it does rely on many actual fields to be simulated throughout the simulation. So here we've got a laundry list of various fields, either scalar or vector valued, that can be associated with either mesh elements or mesh vertices or nodes. And so this kind of provides quite a bit of complexity despite being a fairly straightforward simulation problem. We take note that this is a three-dimensional problem, so we have enough complexity that we can really sink our teeth into it without getting too bogged down in some of the additional details of very complex simulation codes. All right, so to start out, we're going to run Lulesh. This is a fairly straightforward problem. We have this available in our Catalyst examples, repo. We're going to use MPI. We're going to use CMake to build this thing with very simple parameters available, very simple parameters that we need to get going, and we're going to run it and hopefully learn something. So I'm going to take the time. I'm going to not take any time to build it. I already have it built now. So we're going to go ahead and run this Lulesh 2.0-8. That'll give us a help. All right. So here we are. -H. All right. So here we have a number of runtime options. We'll come back to these later as we add some complexity to our Catalyst code. Here we can add specifications for the number of cycles, how big our domain should be. We're going to be simulating on a cube, so we just need to specify a mesh size that'll give us a number of elements in each cardinal direction. There's some options for MPI, etc. So we don't really need to worry too much about this for this example. To run this, we're going to set the domain size to 10 by 10 by 10, very small, 1,000 elements sort of simulation. We'll do 30 iterations, and we're going to show the progress. That's going to give us some outputs at every time step. So we're going to go ahead and run that, and we'll get 30 cycles. Runs very quickly on this very small mesh. Fantastic. We're not running an MPI, but you see we have a single MPI task when we run it in this sort of configuration. We see we have 30 cycles. Great. All right. So we have our simulation running. Good to go. This is kind of going to be our baseline. Now that we can start thinking about how to integrate Catalyst into this workflow. So moving on to version 1, our first Catalyst integration. We're going to add a header and a source file that we're going to call Lulesh Catalyst, and we're going to implement a skeleton sort of Catalyst adapter. Here, we're not actually going to pull in the Catalyst library. We're just going to carve out what we call an adapter. This is custom simulation code that is going to be responsible for taking simulation information and turning it into Catalyst input. And we're going to add those adapter functions at the correct spots in our solver loop. There's 3 functions that we really need to worry about here. So we've got Catalyst initialize, Catalyst execute, Catalyst finalize. Catalyst initialize, it executes once at the start of execution, it sets up all of our backend implementation, and it initializes pipelines. Catalyst execute, this can be called every time step. This can be controlled either by the simulation, or it can control itself, how often the catalyst should be executed. And this is actually responsible for passing simulation data and metadata through pipelines. Finally, we've got catalyst finalize. This needs to match up with catalyst initialize. It's called once at the end of execution, and it simply is responsible for cleaning up pipelines. Now, if you want to get fancy, which we will not be doing in this talk, there are two additional API calls that we could implement: Catalyst results and Catalyst about. Catalyst results is a very powerful tool for returning data from our Catalyst pipelines to our simulation. This is what enables workflows such as computational steering and can be very powerful. Catalyst about gives us information about our backend, which we don't really need to worry about right now. We're going to be using the ParaView Catalyst backend for this particular demonstration. But if you want to develop your own Catalyst backend for some complex capability you want to implement, that is something that you have access to with the Catalyst API. I won't be getting into those, but if you're curious about them, let us know. All right, so first step, we need a Lulesh Catalyst header file. This is going to be very, very simple. We're going to implement 3 functions: initialize catalyst, execute catalyst, and finalize catalyst. This is going to be what we call our adapter code. So here, initialize catalyst will call our catalyst initialize function once we actually implement include our API. Execute catalyst will do the execution, and finalize catalyst will perform the finalize step. So this is going to be very straightforward code here in version 1. In our source file, we're going to add a nice little catalyst initialize flag. This is going to be useful later on for giving us the ability to turn on and off catalyst based on our inputs. We are going to have the most simple initialize catalyst. We're going to just write initialize catalyst to the screen and set catalyst initialize to true in this version 1. It's very straightforward. Similarly, execute catalyst is going to check if catalyst is initialized, and if it is, it's going to print execute catalyst. All right, so we're getting a sense for in this, we're not getting a sense for the API, we're getting a sense for where are we going to put this code in our simulation. And finally, we have finalize catalyst. This again will check if catalyst was ever initialized, and it will tell us to the screen to finalize catalyst. Wonderful. Now we need to add our adapter to the simulation loop. Now, as we talked about, we need to initialize catalyst at the beginning of runtime. So we're going to do that as soon as our domain is constructed here in this example. So within lulesh.h, we're going to create a new domain, given a bunch of options, and immediately following, we'll initialize catalyst. We will need to have a matching finalize catalyst. So we'll put that at the very, very end, right before we delete our domain. Great. And then we need to put our execute catalyst within our simulation loop. So here we have a loop over the time steps. We have our time increment, Lagrange leapfrog operation that actually performs the simulation kind of time step. And we have some printing that can be done. And that is where we will execute catalyst pipelines. Fantastic. So if we're all good there, we can go ahead and try to run this. Now that we have a very simple skeleton of where our catalyst components are going to be placed into our simulation, let's see if we can get execute to be called every time step, following an initialize, and finally with a finalize. All right, back to our examples. We have the exact same runtime. Whoops, I need to actually press this. So we have the exact same runtime options. We're going to have and run that. We get a very quick output. Here we have an initialize catalyst, and then every time step we see that catalyst was executed, and we finally have a finalized catalyst here at the very end after statistics have been printed to the terminal. So it looks like we have catalyst executing in the right spot, but it's not doing anything, so let's fix that. All right, version 2. We're actually going to be calling the Catalyst API now. For this, we are actually going to need to modify our CMake to find the Catalyst library. Then we're going to call Catalyst API from our adapter, both in initialize and finalize. We're going to save execute for version 3. And then we're going to update our initialize Catalyst to accept Catalyst scripts. This is where the actual in situ workflow is going to be coming from. So we'll move through those steps and then we'll continue to add some complexity. All right, so we have some very straightforward things to add to our CMake. If we're going to add a CMake option with Catalyst, this is going to mirror our with MPI option. And if we compile with Catalyst, we will find the package Catalyst. This will require that you have the Catalyst built on your system and that you know where the Catalyst library lives. That should be straightforward if you're familiar with the CMake sort of workflow. Similarly, we're going to need to link our library. So we have our Lulesh executable. We're going to need to link Catalyst with that executable. Again, this is not particularly profound CMake, but we try to make this as easy as possible for you. The Catalyst API, the Catalyst library that you'll be compiling against is a very small library. We call this the stub library, and it provides very little in the way of functionality. It doesn't provide a strong backend, which will come from ParaView later on. But this makes it very easy to link to your simulation code. Hopefully, this is all we need. Great. Now we're going to add some Lulesh specific code, the details of which I'm not going to get into because they are not Catalyst related, but we need to get access to scripts. And the way we want to do this here is we want to add a command line option, we're going to call it -x, and pass in a list of scripts. These are going to be strings, which we will interpret as paths to Catalyst scripts that live somewhere on your computer. We're not going to go into the implementation here. At the end of the day, inside of our simulation runtime, we're going to end up with a vector of strings that lives in this object called command line ops. And we're going to have this parameter scripts that will be initialized. And we're actually going to use that sort of as a gate to turn on and off Catalyst. If you don't provide a script, Catalyst will not run. If you provide a script, Catalyst will run. And in this example, we are going to get into some of those details here. Great. So now that we have Catalyst brought into our simulation build space via CMake, we have access to Catalyst headers. Here, we're going to move back to our Lulesh Catalyst adapter code. In our source code, we're going to include catalyst.hpp and catalyst conduit.hpp. These are going to provide Catalyst, the actual functions that we need to implement, that we need to actually integrate into our adapter, as well as access to conduit nodes, which are really the bread and butter of how we are able to move data from your simulation, how we're able to describe data from your simulation for the purposes of Catalyst in situ processing. We'll dig into that a little bit more here. We probably won't get into as much detail as we'd like, given our time constraint, but if you're interested in learning much more about Conduit and all of its capabilities, let us know. All right, looking at our old initialized Catalyst function, we're going to add a parameter. So we're going to change the function signature a little bit to take in one of those command line ops objects. This is going to give us access to our list of scripts that are passed in through the command line. We're going to create a conduit node. We have a wrapper, a thin wrapper around conduit nodes so that we have a nice C++ API that we can provide for Catalyst. This is really, really nice to work with in a C++ environment, but we have flexibility for C as well as bindings for Fortran and Python as well, which we can get into in a future work if you're interested. All right, so the first step we need to do is we need to check if we have any scripts, as I talked about. If our scripts vector is empty, we'll just turn off Catalyst and then we'll be done. That's fantastic. We'll return and then Catalyst initialize will be false, and none of our other Catalyst functions will do anything. So then, if we do have scripts, however, we will loop over them and we're going to put them into our conduit node. So the way that a conduit node works is kind of, if you're familiar with JSON or YAML, it feels like working with a JSON or YAML file where you can have kind of a nested path to data. What makes Conduit fantastic is that you can put arbitrary data into this data structure, including pointers to data, which is really where a lot of the power of in situ analysis is really rendered. So here we're going to create a list node, which is a leaf of our conduit node that we initialize at the beginning of our initialized script. We're going to give a path to Catalyst scripts and then the script name. So the script name can be anything. We're going to call it script underscore and we're going to give an index. That's going to be the name of our script. It's going to be under this Catalyst scripts path. Then we're going to set that list entry to one of our scripts. So we pass in 7 scripts. This will have 7 script objects that are going to be listed under Catalyst scripts. And then finally, we can pass our full node to Catalyst initialize. So here is our first Catalyst API call. Here we see we need to actually reconstruct our node. We need to recast our C++ node as a C node. This is where a lot of flexibility comes from. If you want to get into some of the details of that design choice here, we can do that later. But this will actually give us a Catalyst environment initialized. It's going to return an error code. Hopefully it is a good one. But if you want to add some error checking to this code as well, I recommend you do that. We won't get into that here. Great. So now, because we changed our function signature, we need to go back to lulesh.cc and change our initialized catalyst to pass in our ops object. Here we have access to that in the main runtime. So this is a straightforward thing that we can simply pass to our initialized catalyst. So now we can see simulation data being handed to our catalyst adapter. And that catalyst adapter is taking that information and producing a catalyst environment for us. Now we need to, similarly, we need to match up our catalyst initialize with a catalyst finalize. And so we're going to go to our adapter and we're going to update our catalyst, we're going to update our finalize call. So here, similarly, we have our gated catalyst initialize flag. If we are good to go, we can create a node, another conduit node, pass that to catalyst finalize, and we can check to make sure that everything finalized correctly. This is a little bit more straightforward. We don't have any, there are no required options that we need to specify with our conduit node. But if, for instance, you have your own custom Catalyst backend where finalize might have some more interesting content that some more interesting operations that it needs to do, and it might need some, might need access to simulation data, this is available for you. However, we don't need it necessarily here for Catalyst finalize. Finally, we're actually going to do an error check here. So this is how you might do that here. If our error is not status okay, then we can tell the command, we can tell our terminal that we failed to finalize Catalyst. Hopefully we don't see that. All right, so because we didn't change our function signature for finalize, we don't need to worry about fixing anything in our runtime, in our main loop. But now we can run our simulation with a script. So as we added that -x option to our runtime options list, we can go ahead and try to run Lulesh now with proper catalyst calls for initialize and finalize. And the next step, we're going to get into execute. This is where things get maybe more interesting. Let's just see to make sure that this all works for us. So we have now Lulesh is going to have the same parameters for the solver that we've been using. We're going to add this -x for a script. And if we hit enter, wonderful. We have, looks like we have properly initialized catalyst, we have executed catalyst, and we have finalized catalyst. So it looks like everything is good to go. If we wanted to run that with without that script, hopefully we'll see that catalyst does not get executed. So hopefully our gate kind of works. Wonderful. So now we see that we don't have the catalyst executes call being made every single time step. So now we have this nice little way of turning on and off our simulation by simply passing in a catalyst script or not. Now you might be wondering, where did this script.py come from? And I will admit, nowhere. So if we look at our directory where we're running this from, we don't have a script.py. We have tricked Catalyst into thinking there is a script, which is maybe not what you want to be doing, but since we're not actually running any pipelines yet, we haven't need to worry about it. So we have tricked it into thinking that there is a script so that we could run Catalyst. But of course, our Catalyst execute simply prints that it executed. Now let's move on to step 3, where we actually do something with that. All right, Catalyst 3, version 3, accessing geometry with Catalyst. Now we're going to be implementing our Catalyst execute code. Here we're going to need to capture ParaView, the ParaView implementation of Catalyst. So as I said, the version of Catalyst that we compiled our code against is a stub library that doesn't provide any backend implementation that does anything very meaningful, but ParaView provides a backend for Catalyst that provides access to all of the power and flexibility of ParaView. This is a fantastic capability that can sound like a bear to compile your simulation against because of all of the crazy dependencies that ParaView requires for all of its massive functionality. Catalyst abstracts that away by simply dynamically loading that library at runtime. So you don't need to worry yourself, the simulation developer, with the actual deployment of ParaView. Fantastic. Here we're going to create a conduit node for describing the simulation's domain data. That is the mesh itself. And finally, we're going to use the most simple Catalyst script to write that domain to a VTK file. And we'll check to make sure that our VTK file actually wrote to disk. Now, in order to do this, we're going to need to access our geometry with Catalyst. So what we're going to do is something kind of interesting. So we need to create a conduit node and we're going to actually give ownership of this conduit node to the simulation domain. So here we have our simulation domain, our lulesh.h. We're going to create a conduit node that is owned by the simulation. And we're going to provide a little getter function so that we can return that to anybody who might need it. Now, this node is going to be more or less static after our simulation domain is set up. And this is where some of the interesting power of Catalyst comes in. So within lulesh init, we're actually generating our domain. After our coordinates are computed or are generated for our domain before we begin running our simulation loop, we're going to set those we're going to get to pass pointers to those coordinates to a conduit node. So here we have our M node object. We're going to create a coord sets directory underneath our node with coords, give it a type, and we're going to give it values for X, Y, and Z. So here we're actually going to use the set external call. So what this will do is it'll set a pointer to that array and hand that to our conduit node. Now our conduit node can see the data, and even if that data gets updated at runtime, those updates will be visible to our conduit node. Now we don't need to update our conduit node at every time step. We simply have access to that data as it might be changing. And if for those who have been listening since the beginning, the actual mesh does move in the simulation. So those points will be moved around. Topology will not, so we don't need to worry about changing the size of these arrays, but the points within the array will actually move. And so those will be updated, and those updates will be available through this conduit node. Now, we're going to represent this as a structured mesh. You may have remembered that I said that lulesh actually operates on an unstructured mesh under the hood, but it is a regular cube of elements, and that regularity is something that we can take advantage of, and we are going to handle it here. So we're going to represent this as a structured mesh. We're going to give it the name of our coord set. So we called that thing coords when we built it in the previous slide. And we're going to give it a dimension of each element. So this is actually the number of elements in each direction, X, Y, and Z. Because we're working on a cube, we know that that is the same value in this simplified simulation environment. So now we have a conduit node that knows about our mesh. And that is very powerful because even if it changes, we have access to that data, the same data the simulation is using for running. Excellent. Now we can move into how do we actually leverage that with Catalyst. We're going to go back to our Catalyst adapter, and we're going to look at our execute Catalyst function. We need to change our signature a little bit. We need to make sure we pass in our local domain. So this is going to be where we can access our conduit node that is owned by our local domain. Here we need to set up a Catalyst runtime node. So as with our Catalyst initialize and Catalyst finalize adapter functions, we're going to create a conduit node. And in that conduit node, we're going to provide a bit of a structure. So the structure is going to have a state and channels. The state is sort of a global representation of metadata about what's happening with the simulation. Here we're going to only be looking at cycle and time, so that's the time step and the actual time of each time step. And then we're going to have channels. These channels provide flexibility for representing multiple data structures at the same time. In this simulation, we only have one grid, and so we're going to have a single channel called grid, and it's going to be of type mesh, and then we're going to pass it some data. That data is in the structure provided by that local domain's conduit node. So we can simply take that node and set it equal and pass it into into this kind of greater conduit node structure. And now we are done. We can pass that along to our Catalyst execute, and Catalyst execute will pass that data along to a pipeline, whatever pipeline you specified with your script. So we can go ahead and check the output, the error output, to make sure we're all good to go. If it failed to execute, it'll tell us. Hopefully it won't fail, and we'll be fine. But here we have now how we're able to access the simulation data in memory in Catalyst. So we've taken basically pointers to our simulation domain and passed them along to Catalyst for execution. Catalyst will pass that along to our ParaView backend, and ParaView will reinterpret that data as a BTK object and string that through a user-specified pipeline. So now that we've changed our function signature, we're going to need to update that in our runtime environment. Fortunately, we have access to that local domain object. Pass a pointer to execute Catalyst, and we're off to the races. Oh, shoot, what happened here? I'm sorry. I have a bit of a technical... Here we are. Great. I must have hit page down, my bad. All right, so now that we have our simulation representing our, now that we have Catalyst representing our simulation data, we need to represent it to a pipeline. And these are represented by Catalyst scripts. So these can be generated in ParaView or can be written by hand. Here we're going to need a few components. We're not going to get too deep into what a script looks like in order to keep this moving along. If you're interested in more details about how to produce scripts, we actually have a series of blog posts coming out. And if you're interested in more of this sort of webinar or video content, let us know. So here's our very simplified script for Catalyst. We're going to need a Catalyst channel name, and that needs to line up with the channel that we set up in our execute conduit node. From here, we need to import paraview.simple and produce a very simple pipeline. Here we're going to take advantage of a trivial producer with a registration name equal to our Catalyst channel. So this is actually going to be reinterpreted as a source for that data, which will interpret our conduit node's data as a BTK object for the use in this ParaView pipeline. So we've got an extractor that will simply take that data and is going to write it to disk in a VTPD file format. This is the simplest sort of pipeline. This is a very simple pipeline because all we're doing is taking that and writing it to disk. You might have writers in your simulation code, but you might not have all of the writers available from ParaView. So this might be a great first step. And that's as far as we're going to take our script today. But if you're interested in things like rendering images, performing contouring, integrating over lines, etc., these are all options that are available via ParaView pipelining. And finally, we've got a block of options that Catalyst requires. These are very simple. We have just two options that we're actually going to set. There are more available. We have an extracts output directory, so we're going to set that to datasets, and that's going to inform our create extractor object that it needs to dump our data into a directory called datasets. And then we're going to trigger every time step. So if you wanted to control when this is actually executed, you can do that here. If you'd like to execute this particular script every 500 time steps or every 10 time steps, you can set that here without changing any code in your simulation. This is very powerful because, as you might have recognized earlier on when we were implementing our initialize adapter, you can have multiple scripts, and you might want to run those at different frequencies. And so being able to control them here kind of removes a lot of complexity of trying to figure out what particular script is going to execute on which time step. You can vary a lot of that complexity in this frequency tab. We have users who prefer to change the frequency that Catalyst execute occurs at within their simulation, and that's totally fine too. All right, so now we can run Lulesh with ParaView Catalyst. So for Catalyst to find the implementation, we need two parameters. We need two system exports that will actually tell the runtime where to find the ParaView Catalyst implementation. First off, we need to export Catalyst implementation name ParaView. That'll tell us that we're looking for a ParaView implementation, and we need the implementation path. So this is a path to where the ParaView Catalyst library lives, probably somewhere in your ParaView distribution. But with those two environment variables set, we can go ahead and run Lulesh in the same way that we did previously. Here with our Catalyst script, now we actually need a meaningful Catalyst script, so we'll make sure we add that to our directory. Come back here to Lulesh version 3, and here we have the same runtime parameters, and we're going to run with that script. Actually, we see now that we have a script located in our directory. This is that same script that we described in the previous slide. Great. So now it's going to take a sec to run the initialize to actually load that ParaView script into memory, and we're going to run. Now we've removed that print function to tell us the Catalyst executes every time step. That's to clean things up a bit. But now if we look at our datasets folder, we see we have a collection of VTPD files. Fantastic. So we have one every time step for 30 time steps. And if we take that into ParaView, here we can actually go ahead and open that. So here we're in our Lulesh v3 datasets, and we see we have a collection of 30 VTPD files. Here they've kind of been grouped into a sequence, into a series. We hit OK, and we can hit apply. Great. And so now we have our cube domain. Let's see if we can outline it with the edges so that we can see we have a 10 by 10 by 10 sort of orientation. And we have our mesh actually being deformed. If we go back to step 0, we have our regular mesh. And if we hit play, we can see that the simulation actually will deform the mesh as that sort of set of blast explosion propagates through the domain. So that's pretty cool. But this is not a very particularly interesting color. As you see, we have access to the composite index, which is just a generic option for telling us the indices of our simulation domain. But we don't have any fields, so let's fix that. Great. So now on to version 4. So this is going to be the last additional complexity that we're going to add in this talk. If you're interested in
Corey,
future...
I'm going to interrupt to pass some
All right.
questions.
Perfect.
We're running pretty long, so there may not be any time at the end. So,
okay.
One of the questions is Catalyst self-contained in the sense that it has all the necessary libraries to support both hardware and software rendering for in situ operations?
Do you want me to answer that, or would you like to answer that?
If you know the answer, I know the answer, but if you know the answer,
yeah. So that comes from the ParaView implementation. So ParaView has access to software and hardware rendering, depending on how it is configured for your particular system. If you have software rendering enabled with ParaView, then Catalyst will have access to that capability.
Yeah, and we recently had the capability to actually compile all of that in and switch it at runtime. So you can have, for example, on Linux, OpenGL, EGL, and OS Mesa backends all available so that you can actually switch between them.
That's pretty cool.
And then there's another question, which is maybe a complex question to answer here, but we'll see what you think. Has anyone tried using Catalyst results as a basis implementation for co-simulation, i.e. multiple discrete simulations running and exchanging data at described increments?
That is a very cool conceptual idea. I'm not familiar with anybody doing that today, but what that would require would be a simulation acting as a Catalyst backend and another piece of runtime running as sort of the producer of that data. Sounds cool. Let me know if you do it, and I would love to hear about those that kind of success. But we don't have any specific examples of that happening yet.
And by the way, I would also suggest looking at Adios for that sort of code coupling, because it is designed more towards this use case.
Yes, I completely agree.
That was
Awesome.
it.
That was it. Perfect. All right, let's finish this up. We got about 10 minutes left. I think we can do it. So version 4, accessing fields with Catalyst. So here we're going to extend our Conduit node to include our field data. And further, we're going to add a couple helper functions to help format scalar and vector valued fields. So to produce a conduit node, a field in a description in a conduit node, here's sort of the layout. We're going to need a fields subdirectory or fields branch with the name of our field. So here we're going to say energy. It's going to have an association, a topology, and the actual values of that field. So the association here for energy is element as opposed to node. The topology is going to be our mesh. So this is going to be a key that will plug into one of the data objects that you have represented elsewhere in your conduit node tree. And then we have another set external call. This is going to pass a pointer to that energy field data array to our node. So this is how we would do scalar valued fields. But remember, Lulesh has a ton of fields, and some of them are scalars, some of them are vectors. So we don't want to hard code this, 4 lines of conduit node representation for each one of these. So we're going to write some helper functions to help us organize all of this data. So we're going to write a add field function, and that's going to take in a conduit node of the name of our field, the association of our fields, that element or node, as well as the actual vectors. It's because this simulation uses vectors for its fields. We're going to pass in a reference to the field itself. Here we've got our association, our topology, and our names, similar to how we described in our in the previous slide here. We're going to pass these all in together. For our uses, we only have one topology that we care about. So we're going to hard code mesh, that one mesh key, so that it lines up with the mesh that we have represented elsewhere in our node. Great. That's how you do scalars. How do we handle vectors? In a fairly straightforward manner, as it turns out. So here we have an X, Y, and Z field that we're going to pass into our node. If you had, for instance, a more complex organization of data for your vector valued fields, we would need to it would need to be supported in a slightly different way, but we can talk about that for future reading. Here we similarly have association mesh, but now our values are actually going to be broken up into a U, a V, and a W component. These can actually be replaced with X, Y, and Z if you're so inclined, or with numeric values 0, 1, 2, 1, 2, 3 if you're Fortran minded. And these are actually extensible to any number of components, which is very useful for tensor valued fields. We don't have any of those here, so we're not going to worry about a generically powerful way of adding fields of arbitrary component numbers. So with these two add field helper functions, we can go ahead and update our conduit node. So again, because these field arrays, the arrays that represent these fields are not changing in memory, but the values are obviously changing throughout the simulation, we can pass a pointer to them at the time we initialize our domain. So similarly to how we initialized our simulation mesh, we can initialize all of these fields on our node owned by our mesh data structure with all of the various fields. So we got a ton of them. Great. So this will actually produce our data structure before the simulation ever runs, and then we'll have access to that data as it changes in memory over time. Fantastic. Now we can go ahead and run again. So this is going to be our last demonstration. Looks like we've got about 5 minutes left, 6 minutes maybe. So hopefully we've made a decent time on this. So running Lulesh with ParaView Catalyst, fully implemented, full integration of your own Catalyst adapter. All right, and now we go back to our code here. Lulesh version 4. We have that same script in this directory as well, just copied here. And we're going to go ahead and run it. This will take just a sec. And then we get 30 time steps, and we are done. So now we can go ahead and go back to Catalyst, or back to ParaView. We're going to delete our version 3 here, and we're going to go ahead and open our new data set. So here we're in version 3. We're going to go to version 4. Data sets, similarly, we have the exact same data organization that we had with our version 3 adapter. I'm going to open this, hit apply. I'm going to look at it with edges so that we can see. But if we go up here to the top and actually color by one of our fields, we can go ahead and take a field such as velocity and actually see that our data was passed through. This is the very last time step. So we go back to the beginning and we hit play. We can see that this explosion sort of starts to propagate through our domain. We're only running 30 time steps, so it doesn't get very far. But if you wanted to run this for longer, that's just a simple command line option. Incredible. So thank you all for sticking with me. We made it through our first Catalyst adapter. We now have a fully integrated, full Catalyst integration into a simulation code from scratch. But now that we have this very powerful tool at our disposal, we've obviously not taken advantage of any of the power of it. We've used it as a glorified writer in this example. So what can we do next? Well, first off, I recommend taking a look at
Corey, hey, Corey, I'm interrupting you with a good question.
Oh, that's fine. No worries.
It's what if the domain was decomposed on multiple processors using MPI? What modifications
I recommend
we need to include?
You try this example with MPI turned on. So one of the fantastic capabilities that Catalyst brings to the table is that it is built for MPI-based simulation parallelization from the ground up. If you have a simulation domain decomposed onto multiple MPI ranks, and you run this exact code on each rank's data will be passed through Catalyst, and ParaView on the back end will interpret that correctly and will produce a partition data set that represents your data faithfully. There's a lot of complexity that you can get into there if you are using, GPU parallelization. Things get a little bit more complex. If you're using, if you have more complex data structures that might be parallelized in interesting ways, things might be a little bit more interesting. But out of the box, if you're using MPI, it should just work. Is that the only question, Berk?
Yep.
Good to go.
Yep.
All right, perfect. Cool. So let's get into the last little bits to close off this. So there is a version 5 actually available on the examples available in our examples. We have this described at kitware.github.io/ParaView Catalyst. This actually has this entire walkthrough spelled out in quite a bit more detail with links to necessary reading for building things like ParaView, building Catalyst out of the box. I didn't get into any of those kind of build questions here, and I know I glazed over some of the details about Lulesh itself. Those are described in more detail here. And if you want to clean up our Catalyst adapter, make it a little bit more user-friendly, remove some of that reliance on those system variable exports, I recommend going and reading on that. But we can get even farther. So making custom pipelines with ParaView is actually fairly straightforward. So using ParaView, you can set up a pipeline within ParaView. For those of you who are familiar with using ParaView, this is the whole bread and butter of using ParaView, are these great pipelining operations. And you can generate very complex pipelines to do very interesting rendering, interesting kind of integrations, interesting analysis, etc. And with a single button press, really, you can generate a Catalyst script with significantly more complexity. I don't want to get into that today, but if you're interested, please let us know. I'd be happy to run another one of these about generating more powerful Catalyst scripts. But as you see, those ParaView Catalyst scripts are just Python. And so we actually can generate entirely bespoke pipelines using Python. We are not limited by the ParaView's understanding of the data. We can actually take advantage of very powerful scientific computing libraries such as AI, ML capabilities, NumPy, SciPy, getting into all kinds of interesting, powerful workflows that are not available necessarily out of the box with ParaView. We can simply import those functions or import those libraries into our Catalyst script and use them operating on our data using the same hardware that our simulation is running on in situ. That's pretty exciting. If you're interested in learning more about that, please let us know. We have a series of blog posts coming out about generating ParaView-based Catalyst scripts. But if you're interested in sort of more detailed, in a more detailed look at using ParaView, or about using these Python like ParaView agnostic capabilities, please let us know. Finally, ParaView is a backend for Catalyst, and we have implemented Catalyst into our simulation. We could go ahead and use any of a number of backends. So available are, for instance, Ascent. For those of you familiar with the Ascent in situ library, we actually have a backend available for that as well as Audios, which gives us access to sort of an in-transit, a very powerful in-transit capability using Catalyst. And with that, I recommend you to go and check out our new Catalyst website. We have this full walk through in quite a bit more detail written out there, as well as a number of other resources for your perusal. Please go please go check that out. And if there are any issues, let us know. We'd love to add more to this website. We want it to be like a great landing page for those of you who are interested in situ analysis. And finally, we at Kitware can be your partner if you are interested in working with us to integrate Catalyst into your simulation code, or if you need help with things like ParaView, or maybe you're interested in courses for your organization. These are things that we are happy to help with. Please let us know. You can get in touch with us at kitware.com/contact. And with that, I want to thank you all for coming. Are there any final questions in this -2 minutes that we are over?
There's one question, which I think we will defer, but I just wanted to mention it. It's, do you know anything about Unreal Engine, Unity, Omniverse? The answer is yes, but I think this is probably being asked in the context of Catalyst.
Mm-hmm.
The short answer is that anything that has a Python interface can be accessed through Catalyst. And I will say vice versa. So therefore, Catalyst and ParaView in general can certainly be integrated with Omniverse. There has been some work in that space. Actually, Media is working on some information about VTK integration, some work on VTK integration. And the Unreal Engine and Unity could potentially be accessed through Omniverse. And if I'm not familiar if they have Python APIs, I suspect that they would have something. If they do, they could be done. And also things like Anare, which also there's a PyAnare, could also be directly accessed through Catalyst. But I think this is a very deep topic and probably not enough time to answer here. I suggest going on some of our discourse lists and asking there.
Absolutely. Yeah, thanks for the question.
And then one more question, is OpenUSD files be accessible through Catalyst? Well, Catalyst is not really there to open files, but overall, I would say currently there is no easy way of bringing OpenUSD into ParaView. We have work going on with especially Omniverse integration that would make that relatively easy. But those are all in the works and they're not available right now. The other way is possible to get OpenUSD output from ParaView and Catalyst, for that matter, is possible. So I think we should probably stop there. Yeah, maybe wrap up, Corey.
All right. Well, yeah, thank you all so much for coming. Again, hopefully all of this information will be available for attendees. I believe we're sending out a PDF with the slide deck here, as well as there is a survey that will come out, I think, immediately following this. So please fill that out. We really love your input. If you have any specific questions, concerns, ideas for future webinars, please let us know. We're very open and excited to get this information into your hands.